Our next problem involves a circle. And if you need to pause the recording here to read the problem, do that please. But I'm going to jump right in and start working it. So since I'm dealing with circular ripples, I'm going to start by drawing a circle. And basically as the pebble is dropped in the pond, of course you've all seen that, how the ripples expand and the circle gets larger and larger and larger. So we're thinking about one ripple as it expands. If the radius of the ripple is increasing at a constant rate of 1 foot per second, so we'll label that radius with the variable r. This information from the problem gives me the rate of change of the radius with respect to time. And then the question, what rate is the total area of the disturbed water changing when the radius is 4 feet? So the question that we need to answer is, what is the rate of change of area when r equals 4? So you start by writing the equation that gives you the relationship between radius and area. So that's a equal pi r squared. Differentiate that with respect to time. And that would be 2 pi r times dr over dt. We're going to substitute 4 in for r and 1 in for dr over dt. So the rate of change of area at the instant that the radius is 4 feet is 8 pi, and the units on that, since it's area, would be square feet per second. So the area is increasing because the derivative is positive at 8 pi square feet per second. The next example is a little more detailed. We have, again, if you need to pause the recording to read the problem, please do that. I'm going to go ahead and jump in and start drawing a picture and organizing the information in this problem. We have a hot air balloon rising straight up from a level field, and that balloon is being tracked by a rangefinder 500 feet from the liftoff point. Here's kind of what we're dealing with. Here's the level field, the path of the balloon, and if our balloon is right here, okay, now I know hot air balloon doesn't look quite like that, but that gives you the point. The balloon's rising straight up, so the path of the balloon is perpendicular to the level field. This distance is going to be a constant 500 feet. There's a rangefinder sitting right here 500 feet away from where the balloon started, and that's not moving. Alright, so reading the next sentence, at the moment the rangefinder's elevation angle is pi over 4, and I'm going to stop right there. Since the problem has mentioned an elevation angle, I know I'm dealing with that right triangle right there. And as the balloon rises, this angle gets bigger. So I'm going to label that with a variable. As the balloon rises, its altitude, or distance above the ground, is also varying. So I'm going to label that with a variable. So let's see. When theta is pi over 4 radians, the rate of change of theta is 0.14 radians per minute. And then our question, how fast is the balloon rising? So that's a question about what is the rate of change of y. So we need to write an equation that shows us the connection between the variables y and theta and the constant distance of 500 feet. And that equation is going to be the tangent is y over 500. Or to make things just a little bit easier so I don't have a fraction, 500 times the tangent of theta is equal to y. Taking a derivative of that then with respect to time, we'll have 500 times secant squared theta times the derivative of theta with respect to t is equal to the derivative of y with respect to t. Now, secant squared is the same thing as 1 over cosine squared. So I can change this to 500 divided by cosine squared of the angle pi over 4 times 1400ths equals dy over dt. And from here, it's just a matter of simplifying the left side of that equation. 500 times 0.14 divided by the square root of 2 over 2, quantity squared. That will end up being 1/2 in the denominator there. And if you multiply 500 times 0.14 and then divide by half or multiply by 2, you're going to end up with 140 for dy over dt. That's a positive rate of change, which makes sense. If our balloon is rising, then y is getting longer. Y is increasing, so the derivative is positive. And we can say that the balloon is rising at 140 units on that would be feet per minute at the time in question. Taking a look at the next example again, pause the recording to read the problem, and then when you're ready, play again.